Hey everyone, I hope you all are doing good. So in this lecture, we're going to be starting with the pigeonhole principle. This is going to be a fairly small lecture, I should say. This is kind of like the warm-up of the more complicated concepts that we're going to be getting into, like permutations and combinations. But this is like a very important principle to understand, and we will solve some very interesting problems on it towards the end too, right? Okay, so let's just quickly go through the definition first, and then I'll try to explain it with some examples. Okay, so according to the principle, if you have n objects, right, and the objects here could be anything. It could be maybe pigeons, it could be maybe apples or maybe bananas, and they go into k boxes. Now the boxes is like just a word we are using. I can say spots or I can use it boxes. So if you have n objects that go into k boxes and the value of n, or I should say the number of objects that you have, is greater than the amount of spots or boxes you have, then at least one box contains two or more objects, right? This is going to be fairly a lot more easier to understand with an example. So let's say you have 5 stars, right? So I give you 5 stars and I give you 4 boxes. Okay, so I'm going to ask you a question, right? Let's say you have 5 stars and you have 4 boxes. Now I ask you the question, can you put each star in an independent box? Like, can you give each of these stars their own box? So try to pause the video and just think about it. Okay, so let's just quickly understand this, right? I have 5 stars. So according to the principle, I can say n is equal to 5. This is my object. The stars in this case will be my objects. I have 4 boxes. So my k value would be 4. If you look at it, according to the principle, the n is greater than k, right? So I can say 5 is greater than 4, which also means n is greater than k. So the principle says if you have objects that are greater than the number of boxes, then at least one of those shares 2 or more objects. So let's just quickly look at it, right? My question was, can you put each of these stars in an independent box, or can you give it its own box? Let's just try to put it. I can put this one in an independent box. Let's just say I've put the first one in an independent box. That's good. I can put the second one in the second box. I can put the third star in the third box. I can put the fourth star in the fourth box. So far it's fine, right? But if you look at it, I have one more star left. So I'll have to put it in one of these boxes. So let's say if I put it in the last one. So what happens is that at least one of the boxes will have to share 2 stars in it, right? And that's pretty much exactly what the principle is saying. So it's saying if you have n objects, which is in our case, it's 5 stars, that go into k boxes. So we have 4 boxes, and the value of our stars is greater than the value of the boxes, then at least one box contains 2 or more objects. So in our case too, I could give the 4 boxes in the beginning their individual boxes, but then I had one more star left, so I had to put it in the last box. So this one, 2 stars in it. Right? This is like a very logical principle, right? I hope this kind of makes sense with an example. We'll take a look at more interesting problems towards the end of the video, but I hope this pretty much makes sense, right? It's nothing more than that. Okay, you have more objects and you have less spots, so one of those spots will have to be shared. Okay, now I'll try to explain this with an animation. I hope that makes sense, and then we'll move on to the generalized version of the pigeonhole principle. So let's just watch this, right? We have 6 balls and 5 boxes. First 5 balls drop in perfectly, 1 ball in each box. So far, so good, right? But here comes the 6th ball. It has nowhere to go. So it has to double up, no way around it. And that's basically the pigeonhole principle in action. So now let's talk about the generalized version of this. Okay, everyone. So I hope you were able to understand the animation. Now let's take a look at the generalized pigeonhole principle, right? Once again, this is going to be a very logical concept to understand. I'll try to explain it with an example, and then I'll be giving a bunch of questions for you guys to solve, right? I think if you solve those questions that I'm going to be giving after this, it will make a lot more sense. Okay, So the idea is if we put n objects into k boxes, at least one of those boxes contains n by k objects. So if you remember in the last part, right, we considered at least one would have two or more objects in it. In this case, we are telling the formula for it. I'm saying it would have n divided by k to the ceiling function. This over here is pretty much the ceiling function, right? Let me just quickly explain what the ceiling function is. So if you have, let's say, a value 3.5 and you apply the ceiling function to it, this basically means it will be 4. I'm saying whatever the decimal value is, you basically bump it up to the next possible integer using the ceiling function. So if I give another example, let's say I have 2.1, right? If I use the ceiling function, this would be bumped up to 3. So I hope this kind of makes sense, right? Okay. So let me just quickly go through the definition once again, and I'll explain it with an example. If we put n objects, so you have n objects, and you try to divide them into k boxes, at least one box would contain n divided by k to the ceiling objects. So the idea is that you're equally trying to divide the objects into spots, and we are saying that if you try to do it and the n value is greater than k, at least one would contain n divided by k to the ceiling function. So let's say, let me just try to explain it with an example, right? Let's say you have 50 people and 12 spots. Okay, so let's say you have 50 people and 12 spots. Then at least one box contains how many? Okay, try to pause the video and answer this question. Okay, so the answer of this question would simply be, it would be 50 divided by 12 to the ceiling function, which would basically be 4.17 to the ceiling, which is almost 5, or I can say equal 5, right? So it basically means I would have at least one box with 5 people. Okay, let's try to understand this and like logically how this works. So my question was, let's say you have 50 people and I ask you the question, I'm giving you 12 spots, right? I want you to divide these people or spread them out into 12 spots. So then how many, at least one box, or I should say spot, would contain how many people, right? Now, according to this function, I divided 50 by 12 to the ceiling, it gives us 5. But let's understand it with actually like what we are doing, right? If I have 50 people, right, I can write 50 as 48 plus 2, right? I'll try to explain why 48. 48, if you think about this, right, I can divide it by 12. So this would give me 4 people. So what I'm saying is I have 50 people. Let's just figure out a spot for the 42 first, because 42 is divisible by 12, which gives us that I can put 4 people and I can spread 4 people out equally in 12 spots. So that would cover our 48 people, right? But then I would have 2 people left, right? And that's the interesting part. So I have these 2 people at the end and I need to find a spot for them as well. So what I can do is I can just equally divide them further, and whatever spots I have, maybe I can add them once again to the beginning spot or some end spot, right? But the point is, then after spreading the 48 people across the 12 spots, I would still have these 2 people left. So I would have to spread them out or add them to some spots. So that would mean at least one of the spots will have at least 5 people, right? That's exactly what this principle means. So that's why we use this ceiling function, because that's what kind of helps us in whatever extra amount you have, you also need to account a spot for it. And that's exactly what the ceiling function is pretty much doing, right? So I hope you were able to understand this function. Now I'll be giving a bunch of questions for you guys to solve. Let me show you guys the ceiling formula visually. So let's consider we have 23 cookies and 4 boxes. Let's spread them out evenly. So that's 5 per box, which means 20 are placed. But we have 3 cookies left over. So let's just try putting them all in one box. So that box now has 8 cookies, right? Or what we can do is we can spread them all out evenly. So 3 different boxes, each gets a 6th cookie. But if you notice, either way, at least one box has 6 cookies, right? That's ceiling 23 over 4. So general rule is n objects, k boxes, at least one box gets n over k. Okay, everyone. So given these questions on the board, try to pause the video and solve them. Okay, so I hope you have solved all these questions. If you were able to, that's pretty good. But they're not that difficult questions. From the next video, we will have like more tricky questions, I should say. Okay, so let's just start with the first one. 30 students in a class, what's the minimum that share the birthday month, right? Once again, this is pretty much the question we just solved. So the formula is the ceiling function n divided by k. So let's just figure out what's n and what's k, right? You have 30 students and you have birthday month, right? We're trying to put students in what their birthday month is. So students in our case would be our n. And what would be our k? K would be the months, right? And we have total 12 months, so that would be 12 in this case. So this would be 2.5 to the c, and this would be 3 as the final answer. Yeah. So what this would mean is that there's at least 3 people that would share their birthday month, right? Let's just try to understand it from a different perspective, right? Let's just logically understand this question. So I'm asking you, you have 30 students in a class. What's the minimum that would share a birthday month, right? Like, what's the guarantee that they would share a birthday month? So let's just take the worst case scenario, right? First, let's take the 12 people out of the 30, right? We can say that, okay, out of these 12, they're all born in different months. Then we take the next 12, so you have 24 people. That means, let's say 2 people are in January, 2 in Feb, 2 in March, April, May. Every single month has 2 people, right? That would be 2 people per month. That means 2 people per spot. So 30 minus 24, you would still have 6 people left. So it kind of relates to the last example we covered, right? We could give 48 people and we could equally divide it by 12, giving them, I should say, 4 people are spread out equally and 4 people in each spot. In this case, 24 can be divided equally, giving 2 people each month. But then you have these 6 people left, right? So these 6 people would have to be further spread out across the months. So there would be at least 6 months, I should say, or there would be at least 1 month where there's 3 students that are sharing their birthday, right? It's just that we're considering the worst case scenario. Maybe it's 5 people sharing the birthday month, maybe it's 4, maybe it's 5, or maybe it's 10 people that share the birthday month. But the idea is that we are sure that 3 people at the very minimum would share their birthday month, right? Okay, so let's move on to the next question now. A drawer has red, blue, and green sock. How many must you pull out to guarantee a matching pair? Okay, once again, let's just logically try to think about this, right? Okay, now the idea is that you're in the dark. You cannot look at what the sock color is. You don't know exactly what's happening. But all you have to do is you need to tell how many times blindly you will have to take out all the socks, such that like how many times you would have to do it, you can guarantee that you have at least one pair, right? Guarantee you have a matching pair. So let's just think about this, right? The drawer has 3 different types of socks in it, which has red, blue, and pretty much green. So let's say you just blindly try to take out, right? In the worst case, the first one would be red. So worst case, first one would be red, and then you try to pull out the second one. In the worst case, second will be, let's say, green or blue. So let's say it's green. And in the third one, let's say it's different one again. So in the third case, it's blue. But now think about this, right? What happens when you take out and pull a sock for the 4th time? So try to pause the video and think about it. Okay, so if you try to pull out a sock for the 4th time, right? It's a guarantee that it will be either red, green, or blue, because that's the only 3 numbers that we have in the drawer, right? So if I pull out for the fourth time, fourth guarantee. So the answer to this question will be basically 4. Answer. Okay, so 4 will be the answer to this question, right? Once again, the idea is pretty simple. So the question is saying that, let's say you're in the dark, you cannot see what's in the drawer, and nor can you see what socks you have taken out from the drawer, right? The question is asking how many must you pull out to guarantee a matching pair. So even let's consider the worst case, right? First time I pulled a red sock, second time it turned out to be blue, third time it's green. But when I pull a sock out from the drawer for the fourth time, it's guaranteed that it will be one of those socks. So I'll have a complete pair of socks in the fourth time. It is guaranteed, right? Okay. Now let's look at the last question, which is pick 5 numbers from 1 to 8 and prove 2 of those 5 you pick will add up to 9. So this is again like a very interesting question, this is the difficult one from this, right? Okay. So first of all, you've been given numbers from 1 to 8 and they're saying prove that 2 of those will add up to 9. So let's just take a look at the set of numbers from 1 to 8 first. Okay, so if I ask you to make pairs of how many of these would add up to 9, let's just make all those pairs, right? I would have 1 comma 1 comma 8 add up to 9. Then you have 2 comma 6 add up to 9. Then you have 2 comma 7 add up to 9. Then you have 3 comma 6, and you have 4 comma 5. Okay, so these are all the pairs that would add up to 9, right? The question is saying that you pick 5 numbers from 1 to 8 and you need to prove that 2 of those you pick will definitely add up to 9. Let's just think about this, right? Now think about these pairs as actual boxes and your 8 numbers as or I should say your 5 numbers as the actual objects that you're using. So in our case, 5 numbers are objects, 4 pairs are our boxes. So let's just think about this, right? Now you have all these pairs. If you try to pick out 5 numbers, it's a guarantee that at least 2 of them will add up to a 9. So if I pick out 1, let's say I picked out 1 over here, right? 1 would go to this box. In the worst case, let's say you picked out the second number is 2, and then the third number is 3, and the fourth number is 4. Now when you pick out the fifth number, right, it will be one of these 5, 6, 7, 8. So if you picked out 5, it would be added to this pair and it would add up to 9. If you picked out 6, it could be added to this pair and add up to 9. 7 could be added to this pair and add up to 9. And 8 to this pair and add up to 9. So the guarantee is that at first 4, in the worst case, it wouldn't happen. But when you add the fifth number, it is a guarantee that it will be one of these 4 boxes, right? It's pretty much like the object box kind of a question, I should say. Okay, so I hope you were able to solve all these questions. In the next lecture, we will be introducing permutations and combinations.